Hello, everyone. Thanks for joining us today. Today, we'd like to welcome Catherine G. She's a physics PhD student at Princeton, advised by Benjamin Eisenbach and Gautam Reddy. With support from NSF GRFP, she's working on applying ML to complex systems and using non-equilibrium statistical physics to develop new RL algorithms. Previously, Kathy received undergraduate degree in maths and physics from MIT. Today, she'd like to present her work that's published at ICLR 2025. Right, stage is all yours, Catherine.
Thank you so much, Rahul, and also giving me the opportunity to talk about my work. So hello, my name is Catherine G. I go by Kathy. I'm going to talk about our recent work on horizon generalization and reinforcement learning. So this was work done with Vivek Myers at Berkeley, as well as Benjamin Eisenbach, my advisor at Princeton University. And throughout this talk, feel free to interrupt me whenever for questions. Okay. So reinforcement learning, as we know, is appealing for its potential to solve long horizon reasoning problems. But as we also probably know, it is precisely this horizon that also makes solving our problems really challenging in real world settings. So I've shown some examples here, like healthcare, urban planning, robotics, and beyond. Namely, the number of possible solutions to a control problem often grows exponentially in the horizon. And this bottleneck is what motivated us to study a form of generalization that we term horizon generalization. Sorry, figuring out slides. Okay, great. I think that works. So we can think of horizon. Okay, great. So our goal is, can we train algorithms that can generalize over the horizon? And what exactly do we mean here? Informally, we say that a goal condition policy generalizes over the horizon if, after training to reach nearby goals, the policy is more successful at reaching distant goals. So say that we're considering the task of maze navigation. And a long horizon goal is, for example, the rabbit being able to navigate all the way to the purple star in the maze. But if we are only training on these shorter horizon tasks, like navigating locally within the maze, are we able to get successes that propagate to the long horizon? And more generally, we can think of horizon generalization as a type of self-consistency. We're saying that when an RL agent tries to solve a long timescale tasks, are its actions consistent with its knowledge or ability on short timescales? So with this intuition and informal definition in mind, we are going to theoretically motivate as well as empirically demonstrate horizon generalization. So on the theory side, we're going to formalize what this means. We're going to introduce a practically achievable invariance on the policy, which we link to horizon generalization. And then we're finally going to show that this invariance, which we call planning invariance, implies horizon generalization. On the experimental side, we are going to empirically link this invariance and horizon generalization, as well as demonstrate that it is possible in high degree of freedom settings, which suggests that they're suggesting some practical methods to achieve this powerful property. Okay, so a general structure for this talk is we are going to start with defining the actual problem setting over which we define horizon generalization, which is the goal condition reinforcement learning setting. We're going to give some theoretical motivation as well as empirical results. And if there's time, I'm going to show a quick slide on self-supervised goal condition methods that we are also focused on within the group. Great. So let's start with the goal condition reinforcement learning problem setting. So oftentimes when we are trying to solve an MDP, like the one shown here, we don't actually care about necessarily maximizing the exact reward function. Rather, we actually care about completing some task that we parameterize within an arbitrarily expressive reward function. And though this figure suggests, for example, a locomotion task, the goal or task that we care about can really represent a wide variety of problems. For example, it can be get to exposition. It also can be have a correct answer to some problem or place a block in exposition, so a manipulation task. And as you've probably noticed when running RL algorithms, the reward function doesn't just tell the agent what to do, which is, for example, get to goal G or get to some nice state. It also tells the agent how to do it. So going from S to B to G rather than just reaching some state G. And this is not very ideal for us for analyzing or understanding horizon generalization, because there's more going on than completing tasks within some horizon. And what we really want to show is, if we train or are good at goals that are within some short horizon, is it good at goals that are long horizon, and ignoring other types of factors? So is there a simplified reward setting that strictly captures the occupancy of the goal state, or the completion of a task that is just parameterized by G? And a simple answer to this is just to consider a reward function that ends up looking like a Kronecker delta function or similar, where you're just rewarding the agent for being in the goal state. So the reward is just going to be 1 when the agent's at the goal state, and 0 otherwise. Almost by definition, the reward strictly captures occupancy of the desired goal. So a question that you may have is, okay, but isn't this problem extremely sparse, right? Here we're showing a really simple MDP. You can probably just randomly walk to the goal, but if we want this to scale up to really, really hard methods, and this goal is very, very challenging in long horizon, what exactly is going to happen here? However, this goal condition formulation is still tractable. We just need to come up with some creative methods in order to, for example, do hindsight experience, relabeling, et cetera, et cetera. I'll be able to talk about some of these methods at the end of the talk on self-supervised goal reaching that we're working on a lot within this group. Okay, so now that we've introduced this intuition for the goal condition reinforcement learning reward function, we can jump into the full formulation of goal condition RL, as well as nice probabilistic interpretations of the value function. First, I want to note that this is not a new formalism, and also the goal condition sparse reward may not exactly have this form. GCRL has been extensively studied for a really long time, and I've added some references at the top for deep RL works with goal conditioning. Okay, with that being said, we can get into the formalism. So again, there's this sparse reward that in discrete settings is going to look like a Kronecker delta. There's going to be slight modifications when you're moving to the discrete setting, but effectively the essence is just, I'm rewarding my agent only for being within some type of goal state. In addition, we are going to consider goal condition policies. So now it's not just conditioned on some S to maximize reward, it's also conditioned on a goal. And this is important if we want our policy to be able to reach a variety of goals. Okay, so now for the probabilistic interpretation. So if we write out the Q function of this sparse reward, the conditional discounted state, the Q function is going to end up looking like the conditional discounted state occupancy of the commanded goal, where pi just notes that this is conditioned on that specific policy that's defining our Q function, and gamma is our discount factor. And what this equation is saying is that maximizing our value function is going to be equivalent to maximizing time spent at our. This is very clean. So the pros are, this has a simple, nice interpretation that is kind of good for our purposes when we're trying to explain and show this phenomena of horizon generalization. But the cons are, yes, we are working in a very sparse reward setting. And also sometimes our objective is just to maximize reward. Sometimes we might not actually want to get to some fixed goal state, for example, in a video game. But again, in our case, this simple interpretation is very important, generalizing from goals within a shorter horizon to a longer horizon, where a problem setting is literally to reach goals. So with this definition of the problem setting that we're going to consider, I want to pause for questions. Okay, let me see if I can figure this out. How do I resolve if someone raises their hand? Or I guess
I can just talk.
Yeah, just feel free to ask the question. Thank you.
Yeah, sorry. So I work on a slightly different problem. I was wondering your P notation, or what is P in the third term of this equation, just so I follow your notation.
Yeah, so P is going to be the discounted state occupancy. What this is just going to be is I'm just adding up like the probability at ST plus 1. I'm going to be at G, condition on starting at SA, but then I'm just counting by gamma.
Gotcha.
Any other questions?
Yeah, we can move ahead.
Okay, great, fantastic. So now we're going to jump. Oh,
this
sorry, I
one.
see a question in the comments. Great. Give me a quick second. Okay, just to be clear, the setting consists of multiple goals and each goal may have different rewards. Yes, exactly. So the reward function is going to be parameterized by your goal. Great. Okay, let's move ahead. So now with these preliminaries of our problem setting, we're going to jump into the main body of the work, which is horizon generalization. In parentheses, the goal condition setting. So now we can give a slightly more formal, informal definition of horizon generalization. Namely, we say that a goal condition policy pi generalizes over the horizon if training to reach nearby goals, say, if we start at state S, some goal S prime, where distance function refers to some temporal distance, leads to more success at reaching distant goals. We are going to begin with this high-level overview of our analysis, providing definitions for everything, as well as demonstrating that horizon generalization does exist for an actually useful policy. A key mathematical tool that we are going to use to understand horizon generalization is something that we term planning invariance. So informally, this is when a goal condition policy is invariant to planning if it returns the same or similar performing actions when conditioned directly on the goal compared to conditioning on a series of intermediate waypoints. So this sounds like a lot of words. Oh, Raul, I see your question. I'll address it right after I go over these figures. That's a lot of words, but I think this idea is most clear graphically. So an example, we can consider the task of maze navigation. So on the left, the output action, if we condition on the long horizon purple star goal, is to go right. However, the output action when we condition on an optimal intermediate waypoint, the brown star, is going to be down. These two actions are not equivalent, and therefore the policy is not planning invariant. There's some sense that, and I'm using the term reasoning super loosely here, but reasoning over short and long time scales is not self-consistent. On the right, we instead now have a policy that is planning invariant, where our agent is going to output the same action down, whether it's conditioning on this final purple star or what it thinks is the waypoint, the brown star. So in the same way that, say, like an image classification model that is invariant to rotations is going to generalize to images of different orientations, we're going to prove that a policy invariant to planning, like the one shown on the right, is going to exhibit horizon generalization under certain assumptions. So addressing the question that Rose sent in the chat, doesn't it sound more like a hierarchical RL setting? Yes, you can definitely interpret this as the hierarchical RL setting. We are using a very specific definition of planning where you're outputting like one fixed intermediate waypoint, but one can imagine that the output waypoints may live in some latent space, describe some set of states, so on and so forth. We are using this definition of planning because that is what is straightforward for us to be able to show our result. But yes, good question. Okay, fantastic. So now that we've introduced this idea of planning invariance, I'm just flashing on the screen the actual definition, but you can kind of ignore this and just think about the figures with the rabbits navigating through the maze. A question is, planning invariance is going to be defined with respect to some policy as well as a planner. Like a policy has to be invariant to a specific planner, but our planner can be very not good. For example, if our planner is just, I'm just going to output some random waypoint that is going to force you to output a random action, you're still going to see planning invariance, right? No matter whether you plan or not, you're just going to output the random action. So there's some sense we need the planner to actually be good or meaningful. We have a lot of different options here, but for simplicity, we consider a class of planners and policies that we term quasi-metric planners and policies. And what this means is that these planners and policies are just trying to minimize some distance function between state actions and goals, where this distance functions just has basic nice properties that allows us to do some theory. So I do want to stress that while I'm, so just as a signpost, we are showing that horizon generalization exists for meaningful planners and policies with the planning invariance property. And this is going to be the same set of planners and policies over which we do some subset of our empirics. However, I do want to stress that while I'm really happy to answer questions about quasi-metric methods, and I'm going to get to their properties and implications in a second, the point of our work isn't to introduce, say, a new method that like does horizon generalization the best or something. It's just to properly define horizon generalization and planning invariance and show that they exist theoretically and empirically. Great. So that being said, the reason we use quasi-metric planners and policies is that they define a nice structure over state space that is useful for planning, where the definition of planning kind of just drops out from this distance function. So namely, if we imagine this state space as some ambiguous blob of states, and we're mapping it to a latent space with some distance function, a quasi-metric is going to obey three properties. So first, it's going to obey the triangle inequality. So it's going to say the distance from A to C is going to be greater than or equal to the distance from A to B plus B to C. Again, this is a form. You can view this as a form of self-consistency. In addition, the distance from a point to itself is going to be 0, and a distance from a point to a different point that is not itself is going to be greater than 0. And beyond just providing a nice structure over a state space that gives us a good definition for a planner, quasi-metrics actually do show up within the goal condition reinforcement learning setting. So importantly, a really simple function of the goal condition RL value function is a quasi-metric. Namely, it ends up looking like this negative log ratio between these Q functions. And if we convert everything now to the probability distributions, this ends up looking like a minus log expected value of a function of h pi, where h pi is the hitting time, or the shortest amount of time it takes for us to get from SA to G when we condition on some policy pi. So this is nice because we now know how to estimate and interpret this D as capturing temporal distance. If we are able to estimate these Q value functions or this ratio between these Q value functions, we are able to get this nice quasi-metric distance function D. So something that you may notice, there's this weird A prime within this distance function that wasn't really there before, right? I think it's well defined if we have a distance between state action pairs and goals. This A prime is the action taken at the goal. In offline settings, it doesn't really matter that much. In online settings, we can just deal with this with a sampling trick. Again, not super important. You can just ignore it for the purposes of this presentation. So I want to pause again for questions. Oh, yes. I'm so sorry about that. Yeah, the triangle inequality is in the wrong direction. AB plus BC should be greater than or equal to AC. Sorry. Any other questions?
Sorry, I had another notation question.
Yes.
So you denote in the third term P of gamma pi G conditioned on G given A prime. Does that mean what is like how likely am I to stay at the goal if I take action A prime? Is that how I should interpret? Okay,
exactly.
Cool.
Exactly. And the actual object we work with is not going to involve A prime. We can do some tricks to get rid of it, but again, not super important. So just pretend it is not there. But exactly. Yes. Thank you so much for the great questions and also the catch on the triangle inequality. Yep, it is in the other direction. That's pretty important. Okay, cool. So moving on. Given that we have this distance function, our policies and planners naturally fall out. Namely, we can just define our policy as taking an action that minimizes this distance to the goal. And we can define this quasi-metric planner as one that outputs a waypoint W. So we define that as an intermediate state that is en route to a goal. So again, returning to this rapid picture, a planner plan where you input this really far star in the left maze can output a waypoint brown star that is temporarily en route to the goal. So now we have the pieces to give the main theoretical statements of the paper. So we have two main theoretical results that show that horizon generalization exists and is achievable via planning invariance. Our first statement shows that there exists quasi-metric policies that are planning invariant under a planner that was defined as per the last slide that chooses a waypoint en route to the goal. So the informal statement of what is shown here is for every quasi-metric planner, there exists a policy that is planning invariant. And an informal proof is this statement follows directly from the conditions of a quasi-metric, namely the triangle inequality. There are some more complications when we are working with distributions instead of individual states, but the general idea is we can invoke triangle inequality in order to get this planning invariance. Pausing in again for questions. Okay, cool. And as you can tell, it's kind of almost by definition or construction that something like this is going to be true, but we do need this type of planning invariance in order to show our next statement on horizon generalization. Namely, that horizon generalization exists and is achievable via planning invariance plus some other, plus some necessary assumptions. So informally, what we mean by horizon oh, sorry, there is a question. What does the planner mean? Does it mean a model-based setting? Not necessarily. I think you can actually just view the planner as just an arbitrary function that takes in your state and goal and spits out some waypoint. Like here, we are specifically considering like this spitting out waypoint function as one that minimizes like distance from original point to waypoint and waypoint to goal, but you can use something that is model-based to output this waypoint. Okay.
So so I mean, you mean you're trying to generate sub goals?
Yes. So you can interpret waypoints as sub goals. Correct.
Okay. Right. Makes sense.
Okay. So our informal statement is that for a planning invariant quasi-metric policy, optimal goal reaching at short horizons implies optimality at long horizons. And the informal proof of this can just be shown from this figure. So we use induction, and planning invariance is just one induction step. It is saying that, hey, if I'm able to navigate between states that are, say, one step apart, so from S0 to S1, S1, S2, S2, S3, this implies the ability to navigate between states 2 steps apart, S0, S2. And we can continue this induction argument to get longer and longer horizons. As you note, though, for an induction argument, we really need a base case. It's not just enough for us to say, hey, planning invariance allows us to say, you're going to output the same good actions when I'm working at horizon H and 2H. We also need that the policy has to be good within this original ball of horizon H, right? And that is exactly our base case, and also a really strong assumption that we will address in some future slides. Okay, great. So if there are no questions, I'm going to move on to the empirical evidence of horizon generalization based on some of these theoretical results. Specifically, we're going to demonstrate that horizon generalization exists in high degree of freedom settings. So just to quickly recap, we went through the motivation for horizon generalization, introduced some objects that allow us to prove that policies that generalize over the horizons do exist. However, this isn't to say that quasi-metric policies are the only ones to exhibit horizon generalization. So we are going to investigate these properties for various algorithms and formulations within our empirics. Great. So to start, how are we going to measure horizon generalization? In experimental settings, we don't expect our policy to perfectly generalize over the horizon. We imagine maybe each application of the induction argument from small horizon, larger horizon, even larger horizon is going to incur some amount of error, or even maybe you don't have local optimality. So in our experiments, we're instead going to compare the relative success rates at some short training task with horizon H and long horizon evaluation task, i.e. At 2H that is beyond the training horizon. And this is the parameter eta that is in the corner. Great. So I'm going to show some results for some canonical reinforcement learning locomotion tasks. So for our ANT results, which are all run offline, shows that different architectures, like different algorithms, critical parameterizations, and losses are going to exhibit different levels of horizon generalization. So what are all of the methods shown here? In the orange colors, this is contrastive reinforcement learning. In this light blue, this is soft actor critic. And in this purple is a method called CMD1. And the only thing you really need to know about CMD1 is that it is specifically a quasi-metric method that obeys all of these preconditions of our theoretical results. So aligning with our theoretical predictions, aligning with our theoretical predictions, the most planning invariant policy, which is the CMD1, exhibits the most horizon generalization. So it retains success at horizons much longer than the horizons of the train tasks. Again, we are only training on these short 1 meter, 10 meter tasks, and we are evaluating on distances that are much longer than this. Great. In addition, we test this on ant maze as well as humanoid with the hope that moving up dimensions or dealing with these mazes allows us to separate really this generalization over temporal distances from generalization over like physical distances. So what are we exactly looking at here? CRL is this contrastive reinforcement learning method that we're comparing against. CMD is this method with planning invariance. And all these parameters are showing the ratio between the successes evaluated at 2H versus trained on H. And for example, if we look at the 15-meter row on the left, the CMD algorithm retains 93% of the success if we evaluate on a goal 30 meters away versus one 15 meters away. Okay, and finally, something that we also explored within a really simple tabular maze setting with access to an optimal planner, namely just Dijkstra's, is that this concept of planning invariance, which we measure as the fraction of success rate retained without planning. So this is how good is our policy with and without planning as a ratio compared to this horizon generalization parameter eta. And we see that these things are fairly related. However, planning invariance alone does not lead to horizon generalization. If you remember the quick comment about the base case made some number of slides ago, we need the condition that the policy can effectively reach short horizon goals. So this gray point here is just a random policy, always going to be planning invariant because it's just going to have a uniform distribution over our actions, right? And we can see, yes, it is very planning invariant, but you're not going to get this horizon generalization. So this additionally shows that you really do need this base case assumption that you are able to do things well locally before you're able to generalize. Okay, and finally, you might be curious of tasks beyond locomotion tasks, whether they're high dimensional or not. So there's some really cool work done by my co-author Vivek Myers as well as Bill Deng, both at UC Berkeley, that are trying to understand compositional generalization, which includes horizon generalization for robot instruction tasks. So I have been having some issues with sharing this video. Sorry, give me a quick second to oh my gosh. Okay, sorry about that. Okay, cool, this works. So I'm just going to show this video that Vivek posted, which is we are giving the robot the instruction, put everything in the bowl, which includes a sushi, a banana, and a corn. However, this task never actually appears within train. The train tasks may include put banana in dish and separately put sushi in bowl. And so this robot is able to show generalization, not just horizon generalization, but also some form of semantic generalization. I'm going to include a QR code at the end for people who are interested. Okay, I'm going to keep presenting. Perfect. So just to summarize, there are rich notions of generalization over the horizon in reinforcement learning. And there are practical methods that can achieve this type of horizon generalization in really high degree of freedom settings. So that is the end of my talk on this horizon generalization work. But I do want to go add on a really quick slide on self-supervised goal reaching methods. So one of the questions that I brought up fairly early into this talk is like, when we're laying out this goal condition setting, it's nice because the interpretation is really straightforward, but there's a question of, okay, this reward is really, really sparse. Do we need to do a lot of other fancy things like intrinsic motivation, et cetera, in order to get a reinforcement learning algorithm to goal reach for a really, really hard task? And the answer from some work within our group is that yes, an online RL algorithm can learn to goal reach just with a single observation of a hard goal state. And I'm happy to talk more about this. I think it's fairly relevant, or even though it's not explicitly relevant to this horizon generalization work within the talk, I do think this idea of representations are a really powerful way to do exploration or reinforcement learning, as well as imposing some structure over representations or a state space via quasi-metrics. So happy to talk about that more. Cool. Okay. I'm happy to answer any questions.
Yeah. Floor is open for Q&A. You can ask. I mean, anyone.
Yeah. Hi. So I would like to start by asking on like the 8 degree of control tasks that you had. You tried on ant maze and humanoid. Are there any other like environments that you think will be viable here?
I think any environment where goals are well defined, like I can't imagine this like relevant. Yeah, I think any environment where a goal is well defined. It doesn't necessarily need to be like a locomotion task. I think even manipulation tasks, like say solving a puzzle. If there's some very complicated puzzle, but we know what we want our end state to look like, you can still formulate this into some type of like goal condition problem. Maybe you need some other things under the hood in order to get this algorithm to work, but
yeah. Cool. So a 2D game like Montezuma Revenge, will that kind of achieve the task kind of here?
So I think yes, if you define a clear goal state, and your goal state might just be, I'm assuming for these games, there's some amount of like reward that you accumulate over the course of this game. An example is you could define your goal state as, say, achieving some base level of reward. Like that is one possible modification to like this goal condition setting that might make sense where you just want to maximize reward. But there is some other active work going on in the group to see how we can just reformulate any arbitrary MDP into a goal condition problem, regardless of whether or not there is a true goal and just maximizing reward.
Yeah, cool. Thanks.
Yeah.
Also, you mentioned that it's a sparse reward setting, right?
Yes.
Yeah. So you said that there is a planner which generates subgoals, right?
Yes.
So are you gonna reward those states, subgoals?
No, we are not explicitly rewarding any state that is within some trajectory. We are only rewarding a policy if it reaches like the final goal within its trajectory.
Right. So Montezuma's Revenge is also a sparse reward setting. So I think we could define some goals over it and then probably can test it out. Sure. I mean, it's a hard exploration problem in RL, right?
Yeah. Agreed. Yeah. I think probably, I do think it is kind of an open question actually of like how useful, like how one should be setting sub goals if you want to solve like really, really complex tasks using these types of goal conditioned methods. I think some of our intuitions for this, like something that we have found within the group is sometimes weirdly, if you only set one desired goal to reach without setting intermediate sub goals, you're still able to learn how to do like fairly complicated things. But agree that probably like some amount of sub goal sampling would be useful.
Also, thanks. I would like to ask, like, how are you generating these sub goals? Like, is there any particular way to generate these sub goals?
Yeah. So, so the sub goals, you can think of the sub goals as being generated by our quote unquote like learned critic, specifically that our learned critic is trying to like output subgoals such that this distance function is minimized from your original point to your waypoint and from your waypoint to your goal.
So my
but
subgoals.
when- oh, sorry. But when we're actually like running our policies, there's no point in which we are generating subgoals. We are not generating subgoals. It's just like our argument with these waypoints and this specific quasimetric setting allows us to prove this property that gives us horizon generalization. But when we actually run these policies, we don't explicitly say, first go to this subgoal and then go to the goal. It's just that these policies have this really nice property that involves subgoals and waypoints that gives us this generalization property.
Okay. Right.
Yeah, there is a quasimetric planar class that kind of is being used, right? So can you like expand a bit on that?
Yeah, so we can view this planner in another way that might make some sense, or planning invariance in another way. Yes, so instead we can actually interpret like planning invariance as, if I apply my planner, like, does my policy change? And we just want to say, if I'm applying my planner, I don't want my policy to change. As in, can I have some policy that it doesn't matter whether or not I plan, my policy is still equally good?
Yeah, so like that sounds like you can generalize based on that.
Yeah, exactly. And that is the result that we show. You can also just view all of this in terms of like language related to Dijkstra's. You can actually view all of this as just like is our distance function or is our learned critic invariant to path relaxation? So this is the recursive step that we are applying when we run Dijkstra's algorithm in order to find optimal paths.
Cool.
Faisal has a question within the chat. Is it possible to extend the analysis to state, action, occupancy? And if possible, what does that imply? Yeah, great question. So some of the extensions of this work for state, action, occupancy are explored by Vivek. I don't think it's on archive yet, but it should be up fairly soon. If possible, what does it imply? So I think, at least for the algorithms we're considering right now, the main implication is, I think we want to, sorry, let me think about how to respond to this. I think it matters because sometimes we actually want to align our occupancy of a future state action with our occupancy of a future state. And I think this can give us some nice generalization properties, but I am going to refer you to some follow-up work. If we only reward the policy when it reaches the goal, does that mean the agent might not learn to reach? Okay, so there's a question, if we only reward the policy when it reaches the goal, does that mean the agent might not learn to reach the optimal states along the way, even if it learns to reach the goal? Is this understanding correct that sparse rewards could lead to suboptimal paths? Should this be considered in the goal condition setting? Yeah, so you're definitely correct. Let's say that, so if we're working in the purely offline setting, like our agent is not going to have access to much beyond the trajectories that we give it. But say that we're working in an online setting, right, where the agent still has an opportunity to actually collect rollouts, so on and so forth. If we're working in the online setting, you're completely correct that if we are running these goal condition algorithms, the trajectories that we get locally might not be that good. Like the trajectories that we get locally could just be really bad, or if you add them together, they form this really circuitous route to the final goal. And I think nothing in our results says that we can necessarily be able to like magically find optimal waypoints if we don't really encounter them during training, like if we don't really encounter them within these local horizon trajectories. That being said, I think when we actually did run the algorithm, we were able to see like forms of generalization that went beyond just, hey, I have trajectory A, can I just like tack it on to the end of trajectory B, we could see like generalization over regions that the agent had never seen before. But it's unclear if that's due to the quasi-metric structure or actually like the underlying representation learning that we were doing for these methods.
Oh, so what I understood is just subcode generation is gonna just help or aid in order to learn your policy. Am I right? But your policy is not inherently dependent on subgoals. It's just dependent on the final code, right?
Yeah. So our claim is that there exist some policies where generating subgoals does not improve your policy.
Okay, that makes
So
sense.
our goal is to construct a policy where generating subgoals does not improve your policy. But agreed, in general, generating subgoals does improve your policy.
So, I mean, if you don't generate subgoals, it becomes a long horizon task, right? As you motivate the problem that long horizon tasks are hard to solve, right? It's a spot towards it.
Yeah. So the idea is doing things like doing long horizon tasks is small and doing short horizon tasks is easy. And presumably doing short horizon tasks, presumably because they're quote unquote easier, we should be able to learn them more readily than long horizon tasks.
Right. Okay.
So Daniel Lawson has a question on how scalable do you think quasi-metric methods are? Have you seen work using them on like environments with image observations? So, so this method, I don't think this method explicitly uses quasi-metrics, but it uses like objects that are fairly similar, and you are able to get like nice generalization within these like robotic instruction tasks. Of course, there's the additional dimension of conditioning with language, but we can ignore that for now. I think the modification from this to using quasi-metrics is not that big, and it should be able to work. But I have not seen myself like fully you're using like a quasi-metric network in order to learn this quasi-metric that is able to do this like complex robot instruction task. Yeah, so hopefully in future work, this robot instruction task will be able to be extended to a quasi-metric method.
Do you have questions?
I had a query regarding hierarchical methods. So, like in the appendix, you try to give a small paragraph of how they can also be used, and like I have used them in the past in RL specifically with representation learning. So, like for the for planning invariance and like try to generalize to reach that generalization. How do you think hierarchy might help?
Yeah, so I think I guess there are two things. First is that if your algorithm does planning, it is going to show this type of generalization, right? Because by definition, an algorithm that plans is going to be planning invariant. But on the other point of like, can we use this type of method where we have an additional like hierarchical RL learning step? Yeah, I actually think that I'd be interested to see work that that instead does this type of like subgoal planning, but the subgoals don't live in actual state space, that they entirely live in some type of representation space or some like set space that like describes some combination of states. And I think the reason for this is like there has been like a lot of prior work on, for example, like bisimulation that's shown that other types of invariances can also help with generalization. And I wonder what will happen if you combine like these other types of invariances via hierarchical RL or other methods with this planning invariance.
Yeah, and specifically when trying to aid in these hierarchies, specifically try to aid in exploration too, and they exploit the metric structure of the problem. So that kind of for policies that we are trying to plan using neural networks as a universal function approximator. So that might be helpful there. Yeah. So yeah, more specifically, I'm rambling here a bit, but uh, if we have a graph structure in which you have suppose edge from A to B that is also trying to reach the sub goal as you alluded to earlier. So yeah, that kind of pattern, trying to detect that and uh, uh, take those policies and like architecturally that might be those sub goals might be helpful in trying to achieve that.
Yeah, like I think a conclusion of this work might actually just be hierarchical RL methods are good. Like that's just one interpretation of the conclusion from this paper.
Yeah, thanks.
There's one more question in the chat.
Oh, yes. Was there a distance threshold for agents to achieve long horizon tasks? Did you see any patterns for failure cases? Yeah, so I think there is a reason why we displayed this x-axis, which is I think if we keep extending the long horizon tasks, like you just get dropping off performance over to 0. And I'm not sure if you would, I guess you could call this a failure mode. It does seem like with every step of induction where you need to now go from your original training state maybe up to 10 meters, then to 20 meters to 30 meters, there's quite a bit of error in every single step of this generalization. I think there's a lot of different reasons that this may happen. I guess we can just say, oh, maybe that's due to say, function approximation or something like that. But I do think there's some issues like within the induction step, as in our representations are still not aligned exactly the way we want them to when we are considering these like waypoints and then these longer horizon goals. I haven't really done in-depth exploration on this, to be completely upfront, but my guess is this is the main thing that we would like to fix. Like, how do you actually ensure that performance over this short horizon does translate to good performance over this longer horizon, beyond just enforcing almost artificially this quasi-metric structure on our distance function. Like, I think the issue there is, like, say we have some short trajectory and then we have some long trajectory from an agent, and both are going from the same state A to the same state B. But one trajectory is really long and one trajectory is really short, and they're all within the same replay buffer, right? It's actually unclear if you use a quasi-metric network, like you're explicitly enforcing your network to be like, this distance function is supposed to be a quasi-metric. Like, which of these trajectories is it going to pick? Ideally, we want it to only learn short trajectories really, really well and kind of ignore any type of long meandering trajectories. But when we apply this inductive bias in this type of artificial way on this network, we might not be telling the agent, we might not be telling our RL algorithm, hey, propagate the induction argument from short horizons to long horizons. We might actually be mixing long horizon data, which might be bad, and short horizon data that is good, right? Which is not really a good thing. And I think that is partially why this we see this type of like drop off in this method. Like, we are not adding any type of explicit enforcement that the priors are propagating in the right way from short horizons to long horizons. Raul has a question, opinion on safety. As this is a sparse reward setting, wouldn't it be hard to navigate the environment safely? Yes, if you train these goal condition methods without any additional regularizers, and you just run this run these online goal condition algorithms on, say, like a robot, you will see the robot like it does things that are like clearly bad and unsafe. Like the robot arm is gonna like twist over itself. It's going to like splay on the ground. It has all these behaviors that are like clearly not good. So I completely agree. I actually think that's from what I've seen, I think there have been some works on this, but applying like safety or robustness constraints in this goal condition setting seems pretty hard, right? Because it seems you have to get a little bit creative, because the basis is that, oh, our reward function is this simple. And our first idea when it comes to addressing robustness and safety might be, oh, we can modify our reward with some other thing that prevents the robot from like doing this crazy thing. But then how do we scale these rewards relative to each other? What exactly does that mean? Question mark. I'm sure there's good work on this out there, but I have not personally worked on it.
Open problems, right? Interesting. Okay, if you don't have any questions, we can wrap the session and thank the speaker. Also, if you have any questions, you can, of course, reach out to the speaker offline. I think she'll be happy to respond.
Sorry for interrupting. Yeah, always feel free to like email me about anything if you're working on something related. I'd also love to know. I didn't show the acknowledgement slide, but I'm going to show it right now. I do want to thank my co-author and also my advisor who's like supported me so much while I've been doing this work. I've added a bunch of like archive links and QR codes. I'm not sure if we share these presentation slides. But yeah, thank you so much for inviting me to give this talk. This is my first invited talk ever in my life, so I'm very happy.
Really appreciate it. Thank you for joining us.
Great.